Hello, hello. How's it going, everybody? We should be live on YouTube, on X. I'm just double checking and making sure it's all working good. Live, there I am. Nice. Welcome, everybody. I am going to hang for a little bit, let some people trickle in, and then we're going to talk about the book that I have tweeted way too many times about recently. Designing data-intensive applications. So, should be fun. Just look over here. Oh, cool. If you guys can hear me okay, someone drop something in the chat. Tell me, make sure you can hear okay, or my comments. There we go. DDIA, let's go. Yeah. Let's do it. Can you hear me okay? I can just turn my volume up here. Check. Nice. Okay, cool. Let's see. Chapter 3. Is it about indexes? It's part of what it's about. Yeah, does talk a lot about indexing, but really it's just about, I actually forget the title at the moment, storage and retrieval. So just in general, how do we store like the table data itself, as well as like how do we index it, do fast lookups, how do we make queries, like how do we lay things out on disk so that queries can actually execute quickly. We'll get into this in a second. Kind of half of the chapter focuses more on OLTP style databases. So, you know, the MySQLs and Postgres and stuff of the world, which is what I'm a lot more familiar with. And then the later part of the chapter focuses more on OLAP specialized databases that do some kind of different, cool, unique things. And I'm like less knowledgeable about those, but we'll talk about them a little bit. Oh, we got a comment from David through LinkedIn. I thought the LinkedIn comments didn't come, but I guess it's working this time. So that's great. Very nice. So how's everyone's day going? I try to, by the way, I'm open to feedback about different times. I figured this was a good time because it can get people awake on the West Coast. People on the East Coast can watch. And even if there's like people that are in Europe, it's not too late in the day to join and watch. So this is kind of what I thought would be a good time, but let me know if there's like better options out there. Okay, cool. All right, well, let's start talking about it. We got like 50 something people here. I'm sure more will trickle in. Last time it was awesome. We got up to like 460 or 480. It was pretty great. See where we get to this time. But for those of you that just joined, what we're talking about today is chapter 3 from this book. If you don't already own it, this is my first time reading it, and I just bought it like, 2 or 3 weeks ago. And a lot of people online seemed really interested. Some own it, some don't. Maybe some people have gone out and bought it. But I just kind of like last week decided, hey, let's do a stream on this. And it seemed to go well. We talked about the first 2 chapters, and I uploaded that video to YouTube. I think you can also scroll back on like Twitter and find it as well. But I uploaded it as an actual video on my YouTube channel. Maybe I should post a link to that over here. So hold on a second, just so you can like find them. So this is the YouTube channel. I don't know if that actually went out to Twitter or not, but it's my same Twitter handle, Ben J. Dickin on YouTube. And that's where you can go and watch these old ones. That's where I'll place the official versions of them after the stream. So, yo, found this channel randomly. I'm in the middle of chapter 2. Nice. So you're slightly behind, but if you don't mind spoilers, hang out for today and we'll do this. Let's see. It's fantastic. EU just after work. Perfect. Perfect. Yeah, so this should be fun, right? My hope is we can go through and do either a stream per chapter, or maybe for some chapters, we can compress them 2 chapters into one stream like I did for the first 2, and just kind of talk about fun tech stuff. So I'm I do a lot of stuff with databases. I work for a company called PlanetScale, and we do like I mentioned before, like MySQL and Postgres, OLTP type databases. But even though I'm in the space, like there's some people that online were talking about like how it might be kind of, a boring book, or you'll know a lot already if you're already in the space. But I've actually found that it's still very interesting, right? Like, yes, there's some stuff that I already know, but I'm still learning some new things for sure. And I like some of the sort of compare, contrast, pros, cons that it does between different indexes or different models of doing databases and stuff. So I'm still learning a lot, and it's still really interesting. So far, I give this book a huge recommendation. I will say, I know they're coming out with a version 2 within like the next couple months. I think it's already out in early release. So I could understand if you want to wait for version 2. The original version was published in 2017. So there's some things that are, changed in the tech scene since then. But great book regardless. So if you do want to follow along with this, get the book, go buy it online, read it, follow along. So anyway, let's talk a little bit. I'll give kind of an overview of the chapter. And again, the other thing I'll remind, I'm totally down to answer questions from the chat, or if you just like, hey, talk about this, or hey, go to that section of the book, say so, and we can jump around. And also, I will mention too, I am, for future streams, I think it would be cool to like get some other people on here. Other people who are in the data space or who use databases, or who are, even if it's not something directly related to like what chapter we're talking about. So if you know people that might be interested, or if you are one of them, send me a DM on X, or somehow contact me. But anyway, chapter 3 of this, like I mentioned before, is kind of the two main competing ideas are the difference between an OLTP database and an OLAP database. Now, I don't know what the audience breakdown is like right now. I don't know who kind of is familiar with those terms or not, but an OLTP database is one that's designed for short transactions, right? So these are, like I said, the MySQLs, the Postgreses, even SQLite falls into that category. There's other proprietary ones like from Oracle that fall into that category. But these are the databases that power your web apps, right? That power Twitter and YouTube and all these things, right? For your interactions, right? That store your login information, that store your account information, that store your chats, that store all the metadata about users and about posts and about all these kinds of things, right? And these databases are it's online transaction processing. So part of the idea is all the queries that are sent to them, for the most part, should be short. The transactions should be able to be processed quickly within milliseconds, or even less than a millisecond, and get back to loading your web application. Because when you're using a web app, you want things to be snappy, you want things to be fast, or phone app, or whatever kind of application, right? Quick transactions, but lots of transactions. In some cases, millions of transactions per second. And then the other category of databases that, like I said, I'm less familiar with this space, but is OLAP. So the A in OLAP stands for analytics. And these are databases that are not necessarily designed to power the actual usability and interactivity of your applications, but these are for analytical efforts, business intelligence, things like that, where you're taking all of the data from your users, from your applications, from your customers, from your products that you're selling, whatever it is, and pulling them into a database so that you can answer analytics questions, answer business questions, answer, what's our profit, or how are we doing compared to last month, or whatever. And that usually requires like doing scans over large amounts of data. What are all the products we've sold over the past year? Or what are all the user posts that, what's the trend of how our users are posting on this platform over the past 6 months, or whatever it is, right? So those are queries that tend to take longer, but it's fine for them to take longer because the app's not dependent on it. This is to answer business questions about what's the next feature that we build, or do we need to price our products more aggressively, all those kinds of things, right? So I'm going to put this diagram. I thought this was a pretty nice diagram from the book here. And this is basically kind of like the outline of, and I think it's using, some kind of like, sort of like grocery store, or some kind of like store that sells physical products as the example here. But basically like, hey, you probably have, in fact, for big companies, you don't just usually have one OLTP database, MySQL database, you often have many of them. You might, again, have one for managing different, your sales application, and one for managing inventory, or maybe a big sharded database for managing your inventory, right? So you might have a bunch of different data sources that are powering either your web application or your inventory management in your store or your phone app or whatever it is. And these are, again, OLTP databases. The way data is laid out on disk, like the whole architecture is designed around, getting inserts, but typically doing a lot more reads than writes. Oftentimes it's like 80, 90% reads, maybe 10, 20% writes, and answering these queries where you're looking for one user by ID, or where you're looking for a very small set of data and returning that back to the user, right? But then when you're doing these analytical queries, you don't want the execution of those to negatively impact the performance of all of these other databases that need to execute really fast, need to answer queries quickly. Because if you have to suddenly do a giant table scan over a table that's, 500 gigabytes or terabyte in one of these databases, that's going to all of a sudden slow everything else down in your app. And there's going to be potential cache thrashing and all that kind of stuff. So oftentimes there's processes to extract data. Maybe it's real time, maybe it's data dumping on a nightly basis, whatever. Extract data from those databases into a dedicated data warehouse type database. And then that is where your data analysts, business intelligence people, whoever, will start to execute queries and, get these analytical answers, right, to figure out next steps in business or whatever. I feel like there's no chats coming through. Seeing a lot of people join, which is awesome. Not very many chats. So I'll remind people, feel free to drop things in the chat. I'm gonna go over here. How do I'm trying to watch my own stream to see what oh, there we go. Nice. Okay, cool. So one of the key distinctions for, okay, this is the what, right? Okay, different types of databases, this is their purpose, but I'm interested in some, we're just interested in the topic, don't want to interrupt. Okay, cool. Well, I'm glad that's the reason. So I figure we could draw some diagrams too, because one of the big differences that is talked about in the book is, okay, so we have these different needs, but how does that impact the engineering of these databases, right? Those two different kinds of needs dictate how you're going to write your data to disk, right? And for the most part, we're going to be sticking with in both of these cases, a relational model, right? Obviously, there are other models we talked about last stream, right? Databases like MongoDB focus on a document model, but we're going to, for simplicity, just think about relational model databases. That's kind of the most common type. But even then, a relational database that's doing OLTP is going to do different things with storing data on disk than a OLAP type database, right? I should have made a table in advance here. This is kind of unfortunate. Why does this look weird? Let's configure. Let's make this look better. I want this. I want this. Just do a regular background here. Okay, cool. So let's do this. Username. Should have made this table in advance. Oh, well. We've got email, and we've got I don't know, address, right? So here we're going to have a table. It's going to have 3 columns. It's really simple, right? But obviously this gets a lot more complex in the real world. So we're going to create a couple rows in this database. I have Ben, hi.com, and okay, let's just say, so we've got this address. All right. You know what I need? I need someone to hop in CalaDraw for me and make the table while I'm talking. We're going to have somebody named Zed. Not feeling very creative right now. Okay, we're just going to do 3 rows. Keep it simple here, and then we'll get to talking. Okay, so we got some data, right? We're in our database. We got some data. Let me zoom in here a little bit. And if this is a table, in our database, when we're doing an OLTP database, one of the things, or the book talks about a couple different techniques for how you would normally lay these out on disk. And some of the popular ways of doing it are either using a clustered index, and this would be a B tree. In fact, B trees are used all over the place in this kind of space. Or another way of doing it is using like heap files and then building indexes kind of separately from those heap files, right? So let's actually look. Okay, this is like a perfect opportunity. I'm going to unfull screen this here. Let's just go over here. Anyone been to, is it B plus tree or bplustrees.com? I forget. Nope, that's not it. B plus trees. Why can't I spell? Oh, shoot, it's down. No. Okay, well, my website is down. So I'm going to go to B trees and database indexes. Okay, I have a website where I actually host just the standalone tool that I used in this blog post to talk about B trees. So apparently something expired or whatever, and I didn't fix it here. Why are these not displaying? Oh, there we go. Okay. So this is a blog that I wrote a little while ago. And again, this tool here, I have these like interactive visuals that you can go and you can basically play around with B trees, right? And the blog itself like talks about B trees. It gives an overview of them, but I also made it interactive where you can be like, hey, okay, so for, let's actually go to B plus tree specifically. You can see like, okay, what happens when you insert things into a B plus tree? You can change like the number of keys per leaf node and per inner node, right? But the reason why I'm bringing this up is because this is the model that a lot of OLTP databases use for storing data on disk. MySQL, which this article was kind of written based on how MySQL does things. Oh, send a link to the site. Sure, I'll try to get my standalone one working. I most likely a certificate expired and I just didn't update it. So that's on me. But yeah, so this is like in MySQL. Every time you insert a row into a table in MySQL, all the table data is actually stored in a B tree. I'm going to make this even bigger here so it's easier to see on the stream. There we go. This will be better. So yeah, all of your table data is stored in a B tree. And like you insert a row, and what it will do is it will take your primary key and it will use that as the key of the database. And we'll put that in here for this B tree. And then your values, like all the row data, like we were looking at before, right? Maybe there's like a primary key that's like an ID or something. And then Ben at hi.com and 1, 2, 3, 4, 5th Street, that's all going to go as the value in here. And the reason why this is often used in the databases space is because when you read and write data from disk, whether that's a solid state disk or a hard drive disk, it does it in pages, which are often 4 kilobytes or might be configured to be 8 kilobytes, but you do it in chunks. You don't just do it like 1 byte at a time. And so you can make it so that your B tree, which if you're not very familiar with B trees, it's okay. I would recommend either reading about them in this book or reading this article or a similar article. You can learn more about them. A lot of you are probably familiar with like binary search trees. They're like an augmentation of that, but to work better with disks because they store multiple key value pairs per node. And so you can size those nodes to match whatever your page size is on your hard drive, on your solid state drive, so that whenever you need to do a search, like I'll simulate searching for 132, whenever you need to like read a node, you can read 1 page off of disk, or maybe it's already in RAM. And then you can search through all the values in RAM very quickly. And then you figure out, oh, what's the next page that I need to read from disk, or the next page that I need to go load. So it's really good for doing stuff that involves lots of I/O, lots of reading and writing from disk. And similarly, when you update your B tree and you need to write, let's say you needed to insert something, well, I guess this is full, but you needed to insert something here, you can write that whole page to disk as 1 chunk. So this works very well, and MySQL does that for all of the data. Postgres does things a little bit differently. The main data file is just kind of stored. They call it a heap file, which I personally think is a bad name because a heap is an actual or I guess a binary heap is an actual data structure. But basically a big array on disk of pages. And that's where all of your row data gets stored in Postgres. And then regardless of whether it's your primary key index or secondary indexes, but every index that's used to look up entries by row, it uses B trees are its main technique. It also supports hash indexes as well, but it builds separate dedicated B trees as separate files on disk. And if you need to do a lookup like in Postgres, if you needed to look up the value, the row that has ID 132, it would load in the pages that it needs from the index file on disk, and it would do this search operation like we see here. And then this value that it finds, value 11, would basically be a pointer into the heap file to say, here's where the current version, actually I forget which version of the row it points at, but here's where that row is in the file. And then it can go look in that file to actually find my name and my email and my address and all those other bits of metadata. So anyway, this good article, I've talked about it on Twitter before, but go read this if you want to learn more about B trees. Again, it's phrased mostly talking about it from the perspective of MySQL. And I made a few changes, like for example, the standard definition of a B tree doesn't necessarily have these neighbor pointers like I'm showing in here. But that's what it does in MySQL. So I kind of tailored this visual to do more closely what MySQL does. But most OLTP databases use B trees for indexes, and they might make their own little modifications for it for performance reasons and stuff. So, however, though, regardless of which, whether you're using the Postgres model or the MySQL model or a different model, one of the things that almost all OLTP databases do is they store your data by row on disk. And what I mean by that is, let's take this column here. I copied over here. So if we think about like the sequence of what things look like on disk, let's see, maybe I'll bring this down to the bottom here. What things look like on disk is it's going to save the string Ben in a handful of bytes. And then immediately after that, maybe there's a separator or whatever. And then it's going to store your email, and then it's going to store Fifth Street. Then the next row in the database is going to get stored here, right? Immediately following that, we have the start of the next row and all of the string data that's in there. And again, these are very simple rows, but you'd probably have, an identifier and all these other things and so on, right? And so then the next row is going to be stored like this, and all the data is going to be next to it. So if we think about your disk as kind of one big long sequence or array of bytes, trillions of bytes, but if you think about it like an array, this is the order that it is storing, those bytes in, right? It stores everything that goes with one row gets stored together, right? This whole row is together, and then the bytes after that are my next row and next row. And if I have a table with 1 million rows in it, we have 1 million rows sort of sequentially stacked together, where oftentimes in OLTP databases, the reason like why they do this is because there's a lot of queries that are like select, star from the user table where name equals Ben, or maybe more realistically, where ID equals 5678. In fact, yeah, I probably should have put IDs in here, but that's okay. Let's put an ID in here because I feel like having an ID is going to be useful for what we talk about, and we've got plenty of time. Why can't I make this bigger? Okay. I need to get better at this. All right, so we'll do that. And then I'm going to just create an ID column here. And we'll say 100, 101. We'll just keep it simple. 1, 2, 3. Okay. So now we have an additional column. I'm going to go put all these values in here. So my ID is 1. We've got ID 2 over with Z here. And then 3. All right. Cool. So like I was saying, in OLTP databases, let's make this go up. I'm realizing my view is blocking your view of this. There we go. There's a lot of queries. Most of the queries are things like select star from user where ID equals 2, right? Or 1,000,000 or whatever. So you're doing a lot of selecting a single row or selecting, maybe 3, 5, 10, 20 rows at a time. And oftentimes you're selecting either all of the columns from that row or quite a few of them, half or more. So if you're doing a lot of select a single row and give me all of the columns from it, it makes a lot of sense to put all of the stuff for a column right next to each other, like we have here. Like that's what you want, because I'm often going to be selecting that whole chunk at a time, or this whole chunk at a time, or this whole chunk at a time. So this is how we lay it out on disk, right? Let's see here. Oh, I might have already answered this question, but I missed this question here. Are secondary indexes, like say on email in this example, also stored on disk? Yeah, typically speaking, if you, again, MySQL, Postgres, these kinds of databases, if you create a secondary index on email, it's going to create typically a B tree, another B tree on disk, and it's going to map the email strings to the identifiers that identify it in the other B tree or in the other file. Yeah. I guess technically, like there's probably some databases that support only in-memory indexes, but typically it's going to be an on-disk thing. Okay, so that is OLT databases. Hopefully that makes sense, like why we store things in that sequence. But the interesting thing is, if you're doing an OLAP database, the kinds of queries that are executed, and again, I'm just saying stuff that's already in the book here. So to get like more details, you can just go to the book. But a lot of the times, the types of queries you run on those analytical databases are not, hey, give me all the columns for this one user. Oftentimes it's things like we were talking about earlier, like I want to know, what was the average profit that we as a company received on every sale that we made over the past month. Okay, so you might have a table in your OLAP style database. So we're still talking about a table. It still looks something like this. Maybe I should use a different example since we're dealing with users and stuff over here. So let's look at this, and maybe we'll add another column here. Say like sign up date. And each one of these will have a sign up date, right? So maybe like 10/25, 2024. And this is the date that you signed up for this application, right? Actually, let's do 2025. No, that hasn't happened yet. Okay, and then we'll do. Okay, so just some made up dates here, right? But you might have an analytical question like, how many people signed up over the past 12 months on our application that live in the United Kingdom, right? Like you're just curious, right? Like, hey, I want to know how many new signups we got in different geographical areas of the world to see, is my app growing faster in the US or in the UK or in other countries? And so you're going to do these more analytical queries. In order to answer that question, and for all different countries, you have to basically scan every single row that was inserted into your database, user creations, over the past year, which could be hundreds of thousands, millions, whatever of rows, right? And then also the other thing about these kind of queries is usually they do not need all of the columns, right? So if I'm asking about the question that I just stated there, what I would want to know is I would need to know sign up date, right? I would also need to know, we're not showing it here, but let's say we also had a country column, right? US, UK, whatever. So I would need to look at sign up date and country column. But really, I don't actually care about the username. I don't care about the email address. I don't care about the street address unless I need to use that to figure out like where they live or what country they live in. I don't even care about their unique ID. And this is kind of a small example, but really this table might have 20, 30, 40 columns on it for a user because there's a lot of metadata you store about your users. So if that's the case, you only need the country column and the sign up date column, 2 columns, but you need to scan 1 million of them. So in that case, if we went back to this model here, that actually wouldn't be the most efficient way to scan through these, because you would have to read an entire row, and I'm not even including a bunch of the other columns there, bring that into RAM, but then only look at 2 of the columns, and then do it again for the next one, right? Read all of these in, only grab those 2 columns that I was looking for, and read all these in. So it's a lot of basically extra disk IO overhead that's just not needed. Makes sense for OLTP databases, doesn't make sense for analytical queries. So what often these do is they use what's called a column store database. And there's a bunch of variations on this. There's some databases that are kind of hybrid. They kind of do column store and they do a little bit of both, right? But a lot of dedicated analytics type databases will not store things based on row. They'll store things based on column. So on disk, I would have scroll down so we can see this better. So I would have, 1, 2, 3, and all the way up to 1 million, however many users I have, all next to each other on disk in a column. And then next to each other, after that column finishes, I would have all of my usernames in one big long sequence and all of my emails in one big long sequence. Probably break this down onto the next line. Hopefully this is interesting. So all these next to each other, and then the sign up dates next to each other. Okay. So hopefully now, looking at this, maybe you're starting to see why somebody would do this. Because if all that I needed was, again, we'll say address is a substitute. Let's say from the address, we can figure out whether someone lives in the US or the UK or whatever country. So all I need to do is I only need to look at addresses, and I only need to look at join dates so that I can make sure it's within the past year, and I can figure out what country they're from. So I can skip all of this IO looking at these other columns that I don't need. And the ordering of these is very important, right? Because if you're going to store rows but not together, you need to make sure the orders line up. So the first value in this, in the address column store, needs to line up with the ID from the first value here and the name and so on. So I know that Ben is ID 1 and lives at this address and has this email due to the ordering, right? But as long as you have that and you can maintain and map things back to their proper columns, now all I have to do is do a big scan over this row or this column to figure out where they live, and a big scan over this column. And if the data happened to be sorted by sign up date, then I also only have to scan subsets of this column and a subset of this column if you know the ordering. Yeah, I have not really a question. So BigQuery, that's Google's big popular analytics type database, uses a column base, if I'm not mistaken. Yeah, so I have not read the BigQuery paper. I actually really want to soon, and we'll share about it. Could even do a stream just on that paper. My understanding is they're kind of a hybrid, like they do clustered columns where they'll like put some columns together, but not necessarily all of them. I could be mistaken there. But yeah, it does use at least some of these techniques. I just don't know the details. You might know more than me. So that would be cool. How cool would it be if we just got like Jeff Dean to hop on the stream and talk about the BigQuery paper? Be sick. Yeah, let's see. Some of the transform in ETL. So that's extract, transform, load. And that's like one of the steps that you would use to pull data from one of your OLTP databases to your analytics engine. As you extract it, you do some transformations on it, then you load it into your analytics engine. Could take care of coalescing in case of missing columns. Yeah, so that transformation stage can like take care of getting rid of data you don't need, doing normalization, all that kind of stuff. That's a good point. So let's see. And then the book too, we won't get into like a ton of detail, but the book also talks about how you can even take this a step further, because, for example, a lot of these columns will have duplicate elements, right? So for example, here, Ben, Zed, and Ali, there's no name duplication, but obviously there's lots of people out there that have the same name. So if I had, there could be like 500 Bens in the username column. And then, okay, Zed's not a very popular name, but maybe there's 300 Alis in the column, right? So you can actually use different compression techniques like run length encoding, stuff like this, create bitmaps to compress these columns down even further. Since you're not storing in this way, you're storing everything in a column that in some cases has lots of duplication, or even like your email. Of course, most people are going to have a unique email, but there's substrings within the emails that are very repetitive. Like there's probably 500,000 @gmail.coms in my user table, right? So there's obviously room for some like string level compression there. Or there's probably lots of people that signed up on the same date. So there's lots of duplicated dates stored in there. So you can do also like a bunch of compression that you couldn't do if you're grouping things by row, which makes, it makes it so that you can kind of store all this data very compactly, which is especially important for an OLAP database, because in these kind of databases often get, if you didn't do compression, often get very, very, very large. Like some companies have petabytes, like the book talks about, of this kind of data, because you might have all of your company's historical data from the past 10, 20, 30 years about purchases, about your user behaviors, right? You're coalescing data from multiple different databases all into one. So these can get really big. And so compression is actually really important in these too, to like keep the space down and to help queries run faster, reduce IO bottlenecks and all that kind of stuff. It's pretty fun. All right. So that was one of the, honestly, that's like a big theme of the chapter. There's lots of other stuff that gets talked about, of course, but is the difference between how you design something at the storage layer, particularly how you store and retrieve data that's optimized for OLTP workloads versus OLAP workloads. So I'm going to look through here. I go through and I highlight or underline a lot of things that I feel like are interesting to talk about. Oh yeah, this was just kind of, it's more of a fun thing. Let me go back over to the book. I think we want to go, yeah. So we need to go way earlier in the book here. I'm going to take this off the screen for a second. I'll find my page that I'm looking for. Where is that? Yeah, this is kind of funny. So earlier on in the chapter, and I see there's a question that came in. I'll get to that in a second. But earlier on in the chapter, they kind of start, or Martin, I don't know why I was thinking Alex. Martin Kleppman starts by talking about just like at its simplest, what is a database? And kind of start by talking about one of the simplest ways to model data that you're storing is as a key value store. And really that same concept is used in B trees and a bunch of stuff in real databases. But you can think about, hey, I have this key, like an ID or a person's name or whatever, and I want to map that to some other metadata information related to that key. And you could literally implement in its simplest form a full functional key value store database in like 6 lines of bash here, right? Basically, every time we want to store something, we're going to concatenate the key value pair separated by a comma to a file. And every time we get it, we're just going to grep through that. We're going to extract just the value out of what we find. And it's possible we find multiple results. So we're always just going to give you the most recent one, which is going to be at the tail of the file. So you could implement a whole database in 6 lines of bash. And this actually works. Like he shows examples of, you can call db set. You can put, information in there with some JSON metadata. You can fetch those things back. And it works, right? So then the question becomes like, why do we overcomplicate databases so much? Overcomplicate databases so much by, having code bases like Postgres or MySQL that are hundreds of thousands or millions of lines of C++. Why do we do that? Well, the answer is like ultimately, one, this is not very flexible. Two, it's not very efficient. It's actually fairly efficient at inserts, right? Just like appending stuff to the end of a file is pretty efficient, although this is storing everything as strings. So in that sense, it's not very efficient. But this is extremely slow to search, because if you have 1 billion records in this file, every single query will have to scan through all 1 billion of those records. Not wise. And this totally ignores things like transactional consistency, right? Like we have transactions in these databases for a reason, right? So that we can group together a set of writes as one logical unit and back off on those if we encounter errors, or commit them if we're ready to commit, right? Like there's a whole bunch of things, multi-processing and multi-threading, like handling those things. Like this is not going to handle well the case of multiple threads trying to change the file at the same time. So there's a ton of stuff that this doesn't do that modern databases do for the sake of performance, for the sake of data durability and keeping your data not getting corrupted, for reliability, transactional consistency, all these kind of things. So I just thought that was kind of a fun way to like, let's break a database down into its simplest possible form. And then we'll start to see as we go throughout the rest of the book, like why this simple form is a horrendously bad idea, but still cool to think about. So let's see. Date compression is really interesting in MySQL. I know very little about that, but that does sound cool. You should message and tell me more, or tweet about it. Let's see. Are column-based databases faster than, say, if I had the required column present as a secondary index in a row-based database? Interesting. Okay. Yeah, this is kind of a so this gets into something that is talked about in this chapter and is a good thing to know about in databases, called a covering index. I think that's kind of what this is getting at, which is, let's go back to here. Yeah, so we talked about like all the reasons why this is good for analytic stuff. But what if I had a regular OLTP relational database like MySQL, but maybe maybe I just needed to like look up, hey, all the users that are within a range of these dates, or how many users signed up between this date and this date, right? Over here, you technically would only need to look at this column, whereas over here, you would still need to like look through all of this other IO that you don't end up actually needing, right? So the question here, and this is a very good question, I'm glad you asked, is what happens if I had a secondary index that just had the dates on it, right? So we'll go back to the B tree. What if this index here, instead of just these arbitrary numbers, like what if all of these keys were my sign up dates? Because you can do that in these databases. You create secondary indexes and say, I want to create an index everything in this table by date. And if you have a query where all you need to know is the date, right? Like, hey, I just want to know how many users signed up between, September and December. You could actually use that. And that's what's called a covering index, which means rather than having to go to your main table data, just one of your secondary indexes, or maybe primary index, can answer the question. Like the index itself has all the information it needs to know. So it can just do B-tree traversal to find it. And the answer is, yeah, that probably would perform a lot better. It would perform a lot better than doing like a big table scan or having to use other non-covering indexes for it. It still probably is more efficient in a column store database, because this probably won't be able to benefit from compression as much. B-tree indexes are not completely full usually, right? Like usually you can see here, there's like some empty space in it to make room for insertions of new keys. Whereas in that column format, we can like keep everything nice and tight and compressed together. So it's still probably going to be faster in the other database, but that is a very good point. We could still make that query go pretty fast over here. Yeah. It's a very good question. Very good question. All right. Go back and look over here. Yeah, we were talking about the very basic database. Let's see, we got a little bit more time in the stream here. So I'm going to find one or two other things that I thought were interesting. I'm curious for those watching. Looks like there's a few hundred people watching. I know. Okay, one of the annoying things about like Twitter streams is I believe when they show you the number of viewers, I believe that's actually the number of people that have viewed at some point, but not necessarily active. So it's hard to know, like, of the 338 Twitter viewers, how many of you are actually here or have left. But oh, well, yeah. So another big important part of this chapter is LSM trees, which we didn't talk much about. So let me just look. Maybe we should spend the rest of the time talking about those. Yeah, that's probably the way to go. So who knows about LSM trees? LSM trees are pretty fun. I'm going to drink some water. So if you haven't, let me, maybe I'll even bring it up here. So I'm going to go find a tweet that I did. Yeah, okay, here we go. So let me just, maybe I'll bring this over here. So a little while back, I read, I guess technically I only read part of it, but the original LSM tree paper, which is very interesting. So this is a type of index, and we'll talk about it more in a minute here. And you can go over here and we'll pull the paper up. When was this thing published again? I forget. Does it say? When was this published? Let's see. Based on when a lot of these references are, I think like early 90s, but I forget the exact time frame. But as you can see, it's a pretty big paper, and I don't think I actually read the whole thing. I read, it's very, 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 very in depth. It goes into arguably much more depth than you need on like extremely detailed time cost comparisons relative to B trees and all this, which is good, like good stuff to know if you're actually going down to the level of you are needing to reproduce the results of this paper and implement it and make a decision. You know, maybe you're an engineer working on a new database engine and you actually need to like decide what kind of tree structure to use. That's great for most people who just want to know like how it works, but maybe aren't going to ever implement it in their lives. It's a little bit dense, but you can still read, like I did, the first 10 or dozen or whatever pages and get a lot of what you need to know out of it. But this is a type of tree that is used generally actually more so for analytics, but also particularly like what this is good at is when it's not even just analytics, but it's when the read-write pressure on your database is a little bit different. So databases that are built around B-tree indexes generally are good for when there's a lot more reads than writes. Like I said earlier, like maybe, you know, in your typical MySQL Postgres database, there's going to be 90% or 80% read queries that are just doing selects and stuff, and maybe 10 or 20% inserts and updates and deletes. So this is really good when you have a lot of sequential data that you need to ingest efficiently, right? Things like click events from a user, you know, streaming logs into a database, other kinds of like collecting metrics on like CPU usage and RAM. That's just sort of a continuous, constant stream of data coming into a database that you need to efficiently get stored to disk, save durably, and then start querying to like show analytics on these things, right? So LSM trees and variants of LSM trees are good for that kind of workload where there's a lot of streaming data coming in that's sort of like coming in a very consistent but high pace, and you need to be able to write those things to disk and then query them. So again, this is kind of like one of the cool things about this book is like, I know about LSM trees because I read part of the paper, and I know about B trees because I've studied them a lot and even wrote an interactive article on them. But there's some cool like talk about the pros and cons and the trade-offs and what kinds of workloads you want to use one on compared to the other. Let's look here. There's a few comments. LSM trees were popularized by Cassandra. Yeah, I am. That's probably true. I don't know a lot about the history. I mean, other than like the paper itself, like what were the first databases that heavily used them? For example, ClickHouse, they have their own modifications to it, but they use LSM like structures. And that's kind of a popular database these days for those workloads that I just talked about, right? Click events, analytics streams, metrics streams, things like that. So yeah. And then let's see. I found the book quite overwhelming at first. Looking forward to the series. Interesting. I'm curious if you have you read the whole thing, or are you just getting started? I could definitely see if you're what would I say? If you're just a younger engineer, maybe you're a student, or maybe you're just newer to the world of engineering and building applications, like this could definitely be overwhelming. It's a lot, right? It's a lot of like really good information. But also I would encourage you power through it. Sometimes with me, like reading a paper, like I talked about when I read this paper a little while back, or part of it, like it's pretty dense. There's some times where I'm reading a paragraph, I'm like, I try to read and pay attention, but sometimes your brain just like glazes over something. But it's like, wait, that was like really good. I need to go back and like reread that or whatever. But sometimes you just power through things. Like, even if you feel like you're not qualified for it or whatever, like power through it, keep reading those papers, keep reading those books, and you'll build that knowledge base. So keep at it. So let's see. Yeah, but one of the, maybe kind of hard to draw. So maybe I'll just borrow some diagrams from this paper here. Yeah, there we go. That's, yeah, we'll use this diagram. It's a good place to start. So the difference between an LSM tree and a B tree has a lot to do with, again, like optimizing for different kinds of read-write traffic. But with a B tree, switch back to this diagram a second, you have these, like we talked about, like your nodes are basically sized according to like what's the size of a page on your disk. And then you are going to like do, a lot of like searches and reads for things. But when you write to things, it's not necessarily the most efficient because, one, sometimes you leave empty spaces for like future reads to go into, or it depends on the order of how things go. Every time you do a write to these, let's like change this. You have to traverse like the nodes that are above it, which might already be in RAM, but in some cases they're not. We can see that like the tree is not fully like compacted. There's a lot of open spaces if we're getting random insertions. So again, great for general purpose OLTP stuff, but not ideal for just, we know we're getting a big stream of sequential data. So what the general idea of an LSM tree is, initially, when you're getting a new write and these big streams of writes, you're actually going to store that into a tree-like structure in memory. Right? So we'll say the C0 tree, this is in RAM, right? And maybe it's a B tree, or maybe it's just some other sort of binary tree-like structure, but something where you can efficiently do inserts and lookups. But you're going to keep it in RAM. And then you'll also, because you want those writes, assuming you want them to be durable, if you don't want them to be durable, just put them in RAM until you save to disk eventually. But if you care about durability, you'd also write to some kind of log, but those are like sequential writes to disk. So those can go very efficient. They're not necessarily fast for lookups, but if you just need to make it durable quickly, you do that. And then for lookups, they can be handled in memory. And then the way that it works is every so often, we can't just necessarily fit our whole database in memory, right? Eventually we have to free up RAM and save that stuff to disk. So every so often, there's essentially like background workers that will take the in-memory data structure and we'll say, okay, we're going to freeze this in-memory data structure. All of our new writes will create now a new in-memory tree that will send those things to. And we're going to have a background process or whatever take this tree and merge it into another tree, either in memory or on disk or whatever, but then save that stuff durably to disk in the form of basically a B tree or something similar to a B tree. But because we're doing this in chunks and we're merging, two trees together into one tree, you can store that much more efficiently. And since these trees are already in order too, when you're doing that merge, you can merge everything in order, make sure the tree is perfectly compacted with no wasted space, and do a lot more big sequential writes of pages to disk, which is generally more efficient, right? So it's actually very cool if you kind of think through the characteristics of how writing happens there. It makes sense why this is going to be like, you might be able to double the write throughput or triple the write throughput or even 10x the write throughput, depending on your hardware and stuff, compared to what it would be like doing the same stuff in Postgres or in MySQL. Let's see. Yeah, and I guess, so then the trade-off is lookups. You know, if you're doing things like select by ID, whatever, those get a little bit more complicated or arguably a little bit slower, because even though you have this stuff on disk and it's very efficient, it's like, okay, you also, the other thing I'll point out is a lot of times with LSM trees, because of this concept of you merge trees together and then trees get bigger and then you merge those trees together. Somewhere in here, I think it has a diagram. Let's find it. Really? No diagram? Okay. Has like a very basic one. But oftentimes you'll actually end up with sort of multiple levels of trees, right? Like you might actually have 5 layers of trees where you have your in-memory tree, and then you have some small trees on disk, and then bigger ones, and then really big ones on disk. So doing searches can become more complicated because it's not one single tree to look through. It's like, how do I know if the record I'm looking for is in my in-memory tree, or if it's in my smaller disk trees that have more recently been compacted, or if it's in my tree that has a lot of my older data that was compacted a while ago. And so there might be multiple tree lookups that need to happen. And then you also have to think about, like, well, if I want to maintain secondary indexes, how do I maintain those secondary indexes and keep them consistent while I'm doing all of this like merging and stuff with my main data? So this is one of the reasons why, again, for like a sort of true typical OLTP workload, this might not be the best, but again, great for logs, metrics, user events, et cetera, that are coming in as a stream. And then if the kinds of queries you're doing over those tend to be more analytical, or, hey, give me all of the results from the past 24 hours kinds of things, you can run those queries over your LSM tree as needed, get that data out, present it to your users, but maybe it's not as much of not as high queries per second demand, or just the types of queries are a little bit different rather than a bunch of random point lookups. So this is it's a really good paper, but like I said, it's dense. So you may, rather than jumping straight to the paper, I'm sure there's other good blog posts out there as well. I would love to, you know, there's only so much time in the day, but I would love to make another version of this B-trees blog post for LSM trees. I think that'd be really cool, but that would be kind of harder, I think, because visualizing LSM trees with this multiple layers of compaction, it's doable, but it's hard to do in the space that you have in a blog. So, and the book obviously like talks about LSM trees, but it doesn't really go into, at least at this point, maybe later in the book it does, but at chapter 3, it doesn't really go into the mechanics of like the details of how it works. Let's see. How does it handle updates? You're probably talking about LSM trees here. It's a great question. Well, for one, I would say it's just a structure that's not optimized for lots of random updates, right? Like if you're inserting, you know, 10,000 rows a second, but you're also doing 10,000 random updates per second at any point in your history, like I'm sure it could be augmented to work well for that, but that's not really what it's optimally designed for, right? It's designed for like ingest a bunch of data, store it to disk, don't modify it all that frequently. I'm sure it can support modifications. It's just not what it's like optimized for, as far as I'm aware. Let's see, when scanning files from most recent to older in the LSM storage engine, so that's like this picture we're talking about here, does the scanner do that based on file names or timestamps? Yeah, that's a good question. And it probably isn't, it depends. Like for all these things, including B-trees, there's the original paper, which by the way, there's also I also recently read the original B-Trees paper. That one's actually very good. It's a lot less dense. Maybe we'll pull that up in a second. But yeah, so I don't actually know. It probably depends on how you want to implement it, right? Like you could always choose where the query planner could assume that you're more likely going to search for a recent record than an old record, or maybe it could just tell by the search that it receives and like figure out like, oh, this looks like it's searching for a newer record. So let's start at the small in-memory tree and go backwards. Or if it looks like it's older data, it could probably start at an older tree and work its way forward. Let's see. So yeah, I think it probably depends. How is the compaction happening? Yeah, I don't think I have time to like fully go into it in here, but basically when you, such a long paper, try and scroll up back to my original picture here. Yeah. So this, I would recommend reading at least the first few pages of the paper, because again, the first few pages are manageable. And you read the whole thing if you want, it's just pretty dense. But yeah, what it's going to do is it's going to take multiple trees that are already sorted and it's going to merge them together. But if you know if you have two trees that are sorted and you're merging it into one bigger tree, you know that you can do an in-order traversal on that tree. And if you just do an in-order traversal kind of on both trees and you track, you're at the in-order spot in both trees and you just check which one of these values is bigger and you insert that one next, which one of these is bigger, you insert that one next, and you can just do that for the entire tree. Oh, I didn't actually put the question up, but it's the one that I'm referring to. So that allows you to create a new bigger tree that is nicely compacted because you knew exactly like how big both trees were originally, so you don't have to like leave extra space open for new records. And so then once you have that committed and written to disk, you can free up the space or the memory for both of those other trees that you had. Yeah. So let's do like one more. I want to pull up since we're on the subject of B trees and all this. Let's look here. Yeah, okay. I'll pull this up. I, of course, will shamelessly plug my own blog post, but what was this? Back in June, I also read this paper. This one's much older than the LSM tree ones. B trees have been known about for much longer, 1970, so 55 years. And this is pretty influential paper, right? Because like B trees are used like in so many databases and stuff. This one is also pretty long, 35 pages, but if you look through, it's it's definitely, it's like probably was written on a typewriter, right? Like it's much less dense. It's a little bit lighter and easier to follow. Yes, there's some math in it. You can just gloss over if you need to, because you can also just kind of look at the concepts and the diagrams they have. So even though it's long, this one's still dense. There's a lot of math, but like I would recommend reading this paper. It's also cool just to go and for historical purposes, right? Like, yes, you can read a modern cool blog on it, which I recommend, but it's also cool just to go like, what were the original author's words, right? And like they probably had, they knew this was a good data structure, but they probably had no idea how influential it was going to be over the next 55 years when they wrote this, right? It's kind of cool to look at that history. Let's see, someone pointed out, and this is probably going back to LSM trees. Updates are basically appends to the in-memory tree and later merged during compaction, and only the most recent update is retained. Oh, okay, interesting. So maybe I glossed over that part. Yeah, merge the files and take the last append value. That could be how it is, yeah. Nice. Okay, well, are there any other questions or like parts I should talk about? I feel like I've talked about most of what I wanted to. This is a good stream. Getting a bunch of buzzes on my phone. Okay, this is a great question. Before you end the stream, are we doing this weekly for each chapter where we read the chapters before the stream? That's the goal. So there are, I believe, 12 chapters in this book. Let me double check. 12 chapters. Yep. It's 12 chapters. This was the third one. So what does that mean? There's 9 left. So over the course of the next 9-ish weeks, it's possible I'll have to skip some, whatever. But over the course of the next 9 weeks, I would hope to do a weekly stream where we talk about the chapter. And if you would like, buy this book. It's a good book. Useful one to have on your shelf. Go get it on Amazon. And you can read the chapters along with me. So my intention is to read chapter 4 between now and next Thursday. And then we'll talk about it on stream again. And yeah, like my hope would be that if there are people that are actually reading along, you could bring questions, right? Have some, notes that you've taken, highlighted some stuff. You can jump on the stream and say, hey, let's go to page 127 and, let's talk about this concept or this data structure or this consistency model, whatever it is, right? So that's the hope. And if you don't want to, or maybe you've already read the book and you don't want to reread it, just hop on the stream, chat, talk about cool tech stuff, databases. That's what I like to talk about. So, okay, I think that's a good place to stop. Thank you, everybody, for coming. This was fun. Very good stream. Like I said, I'll intend to do it again next week. So if you have the book, read chapter 4 and come with your thoughts. Take care. Have a good one, guys.